Hello everyone, welcome to Concepts in Chemistry YouTube channel and also welcome to our new series Chemistry Concept Booster series. So today we are going to discuss 10 questions from organic chemistry, and discussing or solving these 10 questions will help you a lot for upcoming NET, GATE or Barc exam. So I intentionally wrote Barc fast because we all know that Barc exam is in first week of April. So in two phase this time for chemistry, in two phase this exam will be held. First phase in on 2nd April and second phase on 6th April. So in chemistry concept booster series, we already uploaded two videos and we already discussed there 7 questions from physical chemistry. So in this video 10 questions from organic chemistry we will discuss, and I think after discussing these 10 questions, I believe that your concepts in organic chemistry and your solving power of organic questions will improve, and really this video will boost your concepts in organic chemistry. So particularly this video, for obviously this is going to be a Barc special, upcoming Barc special video, particularly for organic chemistry questions. So let's start. So this is first question from organic chemistry, and in chemistry concept booster series it is 7 questions. We already discussed 6 questions from physical chemistry. So this is the first question. So starting material A, reagents, these are the product X and Y. So in the options, if A is acetic acids, then the yield of the products, option A 50%, Y 0%. Option B, C, if A is phosphoric acids, strong acids, acetic acid, weak acids, P2O5 just to remove the water. So if we use option B, if we use A as a phosphoric acid, then X 50%, Y 50%. So in four options, so reagent A is acetic acids either acetic acids or either phosphoric acids, but in the four options the percentage of yield is different. So the options for A is 2, either it's acetic acids or phosphoric acids. We all know acetic acid is the weak acids and phosphoric acids strong acids. So by saying the starting material and reagent is a acid, so I think you all recognize these reactions. It is called Fischer Indole cyclization reactions. So let's see the mechanism and we will explain all the uh, important points regarding these reactions. So this is given as a starting material. So this is a hydrazone. So sorry, one nitrogen should be there. Forward to there should be one nitrogen. So this is a hydrazone. So we can make this hydrazone from phenyl hydrazine and that carbonyl compound. So methyl ethyl ketone. So if we treat this hydrazone with acid, then this two type of indole will be formed. So percentage will be different, but possible indole formation is this two. So these two type of indole will form if we treat this hydrogen with H plus or acids. So now see how this so how the indole is formed. So this is called Fischer indole cyclization. So this is hydrazone in presence of H plus. So first this nitrogen will protonate on hydrogen, and after that there is two way to form the hydrazine. Means after protonation, this methyl one hydrogen from this methyl break and form this hydrazine in, or you can say this portion only in amine. Whole portion is in hydrazine, or you can say this portion only in amine. So this one hydrogen from this methyl group break and form this in amine, or you can say in hydrazine. Or second option is there is CH2Me group that side. So from this CH2 group one hydrogen will break and neutralize the positive charge on nitrogen and form a this enamine kind of moiety, or you can say this whole in hydrazine. If you see the structure of the alkene part, see here this alkene is less substituted, means only one R is there. In this alkene there is two R group, means two methyl group is there. So this alkene is more stable. So this is a more stable in hydrazine, or you can particularly say this portion in amine. So this is more stable, this is less stable, because this alkene is more substituted, this alkene part is less substituted. So in this way, first in hydrazine, or we can partially say this functional group, we can say this functional group in amine formed. So after in hydrazine forming, so then in presence of H plus again protonation will occur. So there is two NH group, one is closer to phenyl ring, one is closer to alkene ring. So many so most of the people think that normally this nitrogen will protonate, because all of them think that this nitrogen lone pair will be normally involved in resonance with the phenyl ring. That's why this lone pair is unavailable. That's why most of the people show the protonation in this nitrogen group, but actually protonation will occur in this nitrogen, not this nitrogen. Protonation will occur in this nitrogen. So the reason is that, so see, if this nitrogen lone pair will involve in resonance with the phenyl ring, then phenyl ring will lose the aromaticity for some time. For some time, if this nitrogen will involve in the resonance with this alkene part, just the stability of alkene for some time lost. It lost its stability for some time. So this is the aromatic ring. If this nitrogen lone pair involved in the resonance with the phenyl ring, then the aromaticity of this phenyl ring will lost. If this nitrogen lone pair involved in resonance with this alkene, thus the stability of this alkene will lost for some time. So this nitrogen lone pair will try to rest on this nitrogen atom. It is not, this lone pair of nitrogen will not try to involve in the resonance with this phenyl ring, because if it involved in resonance with the phenyl ring, then there is a huge loss of energy, means aromaticity of this phenyl ring. So that in that case this whole system become more unstable. That's why this lone pair is more available than this lone pair. Yeah, this lone pair is involved in resonance with this alkene, because just when it's involved in resonance with this alkene, some amount of stability is lost by this alkene. Okay, but if this nitrogen lone pair will involve in resonance with this phenyl ring, then this phenyl ring lost its aromaticity. So most of them shows normally protonation in this nitrogen atom, but actually protonation will occur in the nitrogen atom because this nitrogen lone pair will be more available than this nitrogen lone pair. So normally protonation will occur, and in this case 1 2 3 1 2 3, so 1 2 3 1 2 3 3 3 sigmatropic rearrangement will occur. So now this intermediate form, and this hydrogen break to form this neutral aniline, and this aniline will attack this C double bond imine bond. We all know that CO bond and CN bond are somewhat similar kind of show somewhat similar chemical properties because nitrogen and oxygen are closer to each other in periodic table. That's why C double bond N and C double bond O chemical properties are somewhat similar, so they behave like similar. C double bond end and C double bond O, it is imine. So this NH2 attack this imine, and after that release of ammonia, this NH2 from H, this NH2, and from this carbon 1H, overall ammonia group leaves to form indole. So in this way indole is formed. So now come to the main point. This is the formation of indole, how indole is formed. Now come to the main point. So if this less stable hydrazine involved in cyclization further, then we will get Y indole molecule. If this more stable, because here alkene part is more substituted, if this more stable hydrazine molecule further subject to cyclization, then we will get this X indole. So if this less stable hydrazine will undergo cyclization, then we will get Y indole. If this more stable hydrazine will involve further cyclization, then we will get this X indole moieties. Now see, now carefully listen. I am going to inform you the most important point. So just carefully listen, or you can write in your copy. So acetic acids, there is two options for A, either acetic acids or H3PO4 strong acids. So if we use acetic acids, means weak acids. So acetic acid if we use as a source of H plus, then it is weak acids. So weak acids is, we can say it's weak acids, so it's more selective. So it prefers the path, it prefers the path of any reactions where the more stable intermediate form. So the weak acid means it is more selective, it's less reactive. We can say it's less reactive, it's more selective. That's why it will prefer the path, which path the more stable intermediate form, it will proceed that path only, in which path more stable intermediate is formed. So if we use acetic acid as a source of H plus, since acetic acid is a weak acid, or we can say it is less reactive, it is less reactive, so it is more selective. Since weak acid less reactive, more selective, that's why it select a particular path, in which path the more stable intermediate is formed. So in this case more stable enamine is in hydrazine is formed. So if we use acetic acid as a source of H plus, so it will prefer this path only, because in this path stable intermediate is formed, and if this intermediate is formed, then we will get after cyclization X as a product. So if we use acetic acids, then we will get close to 100% X as a major product. Only more less than 5% we will get that product, because this is a more stable hydrazine, more stable intermediate. Acetic acid prefer to follow the reaction via this path only, not the less stable in hydrazine intermediate. So if we use acetic acid as a source of H plus, then we will get X indole as a major product. Means if we use acetic acid as a source of H plus, then we will get X as a X 100%. We will get X 100%. So we will get X 100%, Y 0%. Why 0% or not 0%? It is more less than 5%, 1%, 2%. Yeah, we will get some amount of Y, but less than 5%. We will get 100% X. Now come to the phosphoric acids. So we all know phosphoric acid is a strong acid. So phosphoric acid is a strong acid. Remember that phosphoric acid is a strong acid. Since it's a strong acid, so it's more reactive. More reactive means its selectivity less. It's less selective. So phosphoric acid is more strong acids. It's more reactive. That's why its selectivity less. So it is less selective. So if we use a H plus source as a if we use phosphoric acid as a H plus source, then since it is more strong acidic, it's more reactive, it's less selective, so it has no time. Phosphoric acid has no time to select a particular intermediate, whose intermediate is more stable, whose intermediate is less stable. It has no time to select the path, in which path if we proceed by this path, then we will get a stable intermediate. If we proceed via this path, then we will get a less stable intermediate. No time. There is no time for H3PO4 to select a particular path, because it is more reactive. Its selectivity is very less. So since we are using H3PO4 as a H plus source, so it's more strong acids, it's less selective, its reactivity high. So if there is possible, there is 2, 3, 4 possible way to form intermediate, so it will lead the it will lead the all paths in same extent. Means it will lead the reaction proceed by all paths in same extent. Means since there are, in this case, since there are two paths, there are two way to form intermediate, so phosphoric acids will let the two paths in same extent, because for H3PO4 there is no time to select a particular path in which path stable intermediate is formed. It is more reactive, its selectivity is less, so it will see there is two path to form intermediate, so it will lead the reaction to proceed in the two path via same extent. So that's why if we use H3PO4 as a acid source, then X and Y will form in equal amount, means 50%, 50%. Weak acid, acetic acids, it is more selective, it is less reactive. That's why it select a particular path in which path more stable intermediate is formed. That path, it will lead the reaction, it will lead for proceeding the reaction via that path only. So that's why we will get X indole as a major, more close to 100%. But H3PO4 strong acid, it is more reactive, it is less selective, selectivity less. So it sees, this acid sees that for this starting material, for this hydrazone, there is two paths for forming in hydrazine. So it will let the hydrazone to proceed via two paths with same extent. That's why we will get X and Y in equal amount. So acid more selective, select particular path, we will get one molecule as a measure, in this case close to 100%. Acid is strong, that is more reactive, less selective, so it will lead both the path for these reactions to proceed. That's why both the enamine or both the intermediate in hydrazine will form in equal amount, and that's why after cyclization we will get both the product with equal amount. So the option is A. If we use H3PO4 as a acid source, then we will get X 50%, Y 50%. If we use acetic acid as a source, then we will get X 100%, Y 0%. So in these three options, there is no option that is X 100% and Y 0%. So in all case, X 50%, X 50%, X 100%, Y 0%. But if we use H3PO4, we will not get X 100%, Y 0%. If we use H3PO4, then we will get X 50%, Y 50%. If we use acetic acids, then we will get X 100%, Y 0%. So these three options are incorrect. Option B is correct. H3PO4, X 50%, Y 50%. If there is if this option is like that, acetic acids, then X 100% and Y 0%, then it will be right. But in that case, H3PO4 and P25 is there. That's why X 100% and Y 0% is not correct. For only acetic acids, we will get X 100% and Y 0%. So this is a very conceptual questions. I think the first questions from organic chemistry in chemistry concept booster series will learn this discussion of these questions. I think you got important concepts, and I think you all understand these questions. So I think you got some very conceptual information from these questions. So let's move to the second question. In this case, option B is correct. So this is chemistry concept booster 8, organic chemistry question 2. In the chemistry concept booster series, it is 8 questions. So this is a cyclohexene carboxylic acids. So I2, potassium iodide, sodium bicarbonate is there. Second, tertiary butoxide, THF. Third, osmium tetroxides, NMO. And fourth reagent is aqueous NaOH. So these are the sorry, I forgot to write the option A, B, C. So you have to assume that this is A, this is B, this is C, this is D. So A, B, C, D. So this is A, this is B, C, D. I forgot to write the option, so sorry for that. So let's move to the answer and see the mechanism and try to understand the use of reagents. And we are selecting this type of questions because by solving, by discussing, by practicing this type of questions, you will be aware of so much reagents, use of reagents, so much name reactions, so much rearrangement. So whole organic chemistry will be covered in this question discussion, in this question discussion series. So let's see the answer. Let's see the mechanism. Then we will obviously we will try to find the stereochemistry also. Just see the answer, try to understand the mechanism. So this is given as a starting material. So I2Ki, sodium bicarbonate, alcohol. So you all know that I2 is given, means there is an alkene part, double bond. So just halonium ion form. Just if we use bromine, then brominium ion is formed, cyclobrominium. So in this case I2, so cycloiodinium ion is formed. So this is, since this is a after forming the iodinium, cycloiodinium ion, it become a cyclohexane. So we have to draw the chair form. So see, this is cycloiodinium ion is formed with the alkene if we use I2. So Ki is a just nucleophilic catalyst, so for these reactions. Now sodium bicarbonate we use, so it's abstract this hydrogen from these carboxylic acids. Now there is two options. In these two options, if this carboxylate anion attack this carbon or this carbon, means path A and path B, there is two paths. If it will attack via path A, then there is formation of 1, 2, 3, 4, 5 5-membered lactone. If this carboxylate anion will attack this carbon, then formation of 1, 2, 3, 4, 5, 6, 7 1, 2, 3, 4, 5, 6 6-membered lactone is formed. So we all know that 5-membered lactone is more stable than 6-membered lactone. So if you don't know, just note the point that 5-membered lactone is always more stable than 6-membered lactone. So 5-membered lactone formation is always favorable. So B path is not favorable. If this O minus attack this carbon, then there will be formation of 6-membered lactone. We all know that formation of 5-membered lactone is more favored. So that's why this O minus attack this carbon and this iodine become axial position in that way. So 1, 2, 3, 4, 5-membered lactone is formed. Now second, they use tertiary betoxide base. They use base. See, there is a leaving group and beta position. There is a exact orientation, means anti-orientation. Anti-periplanar orientation is a hydrogen atom. So there is obviously anti-elimination will occur. If there is a leaving group like iodine, any leaving group, halogen, bromine, OTS, and if there is a hydrogen or deuterium in a beta position with a perfect orientation, means anti-periplanar orientation. See, in this case, anti-periplanar orientation. So alpha beta, there is also one hydrogen in this carbon. There is also one hydrogen, but this is also beta hydrogen, but this is not the this is not in a anti-periplanar orientation. In that carbon, this hydrogen is in anti. One hydrogen is equatorial position, but this axial hydrogen is in anti-periplanar with respect to leaving group. So in presence of base, anti E2 elimination will occur. So this compound will form. So we can rewrite this structure like in this way. So this structure and this structure are same. We can write in a different way. So now osmium tetroxide and in presence of NMO. So we all know that osmium tetroxide will if we treated any alkene with osmium tetroxide, then dihydroxylation reaction. Dihydroxylation reaction in syn manner, it will lead to the dihydroxylation in syn manner. But if there is a steric crowding, then with less steric crowding phase, if there is a steric crowding, then it will prefer the less steric crowding phase for dihydroxylation reaction. Since in upper there is this group, there is this CO, this group, there is also a ring. You can say there is also a cyclic ring in upper side. So osmium tetroxide dihydroxylates via below, not from that phase, above, not from the upper phase. Its dihydroxylation occur from the below phase. That's why we write that OH is below. Now if we treated this whole molecule lactone with 1,2-diol, there is a lactone group. If we use aqueous NaOH, means hydrolysis, then OH minus attack this group and carboxylic acids and OH, it break into carboxylic acids and OH. So OH minus attack this group and this bond break. So this became COOH and O minus take a hydrogen from water. So see, this carboxylic acids is up, this OH also up, because OH minus attack this hydrogen only and this bond break. So this OH will be up as previous. In the product is also it's up. The carboxylic acid group also up, not below. So if we draw normal cyclohexane as a cyclohexane as a normal planar form, then this 1, 2, 3 position OH and carboxylic acid is up, above the plane, and this 1, 2, this 1, 2, 1, 2 diol is in below the plane. So I think you all understand the whole mechanism and the use of reagents. So this is the exact product with exact stereochemistry. So now 1, 3 position OH and COOH up, 1, 3 position OH and COOH up. This OH adjacent OH, these two OH are below. So C product adjacent of that OH, there will be two OH which are in below the plane. So option A, I forgot to write, this is A, B, C, D. Option A is right. So now, yeah, first we have to see the option obviously, then just take the starting material and treat it with the all possible reagent given there, and after that automatically you can find the stereochemistry of the product. So here one point, this is the elimination point has to be noted, that anti-elimination, since there is beta hydrogen and leaving group, anti-planar orientation. Second point is the electron formation, 5-member electron will form, not 6-member. So in this case 5-member electron formation is more stable, we all know. And that dihydroxylation, it will dihydroxylate the double bond below from the below, not up, because in upside there is this group, or you can say this ring is there, that's why steric crowding will be there. So from less inert side, syn dihydroxylation will occur. After that, just hydrolysis. So this is the product. I think you all understand the mechanism. So let's move to the next question. So this is chemistry concept booster 9. So this is also 1, 2, 3 diol in substituted cyclohexene. So these are the reagent: palladium carbon, MsCl, KCN DMSO, divalase. So these are the options. So this is the starting material. Now we have to treat each reagent stepwise to that starting material. We will see later the stereochemistry of the product, or option of the product. Just try to proceed with each reagent, treating with each reagent with this starting material, cyclohexene, 1,3-triol cyclohexene. So this reactant is given in the molecule. First reagent is hydrogen, palladium carbon, ethanol. So you all know this reagent, just hydrogenation will occur. So there is alkene double bond, just they hydrogenate the alkene. So now it's become saturated cyclohexane. This we all know, this hydrogen palladium carbon just hydrogenation occur. Now MsCl, this is MsCl, so methyl sulfonyl chloride. So 2.1 equivalent use means, so this is a just like tosyl chloride, this is methyl sulfonyl chloride, so MsCl. So base is there, this base abstract hydrogen of this two OH group. Since there is 2 equivalent of MsCl, so both the OH group will methylated. So both the OH group convert into OMS, since there is more than 2 equivalent is used. Now after that KCN DMSO is there, DMSO solvent, KCN is there. So KCN is the Cn minus the nucleophile. See, Cn minus exchange is given. So Cn minus exchange means there is a lot of Cn minus. So Cn minus is a good nucleophile, so it will attack that position, so OMS leave, CN attached, but in that case there is no stereochemistry. But in that case, since it is below, so after nucleophilic attack by CN minus, inversion take place. CN will attack from the top side. In that case, this carbon, in that case CN minus attack this carbon, so there is no stereochemistry at all. But in this case, since it is directly connected to the ring, so CN minus attack from above. Since OMS is below, CN minus attack from above, so we will get this type of product after treatment with KCN. In this case, inversion take place. So now if we treat this dicyano compound with dival A's, 2 equivalent, then in low temperature, we know in low temperature CN group transform into aldehyde group. If we treat dival A's, this is the reagent, use of reagent. So I told you that we will learn lot of chemistry from this question discussion series, particularly organic chemistry, lot of use of reagent, lots of name reactions. So if we use dival A's, so this is a reducing agent. So if we use dival A's, so dival A's is a reducing agent, and in low temperature, so with in presence of dival A's, CN group transform into aldehyde group, CHO group. So normally ester, so normally ester and so normally ester group, normally ester turns into aldehyde. Particularly we use dival A's for transformation of ester to aldehyde. But in minus 70 degrees centigrade, cyano group also transform into aldehyde in presence of dival A's. And also for this transformation also there is a need of acidic workup. So this 1-2 step from to convert cyanide to aldehyde in presence of dival A's reducing agents, we need a acidic workup. So this 1-2 step is involved in the conversion of CN to CHO. So so in the product, this is also above, this is also above the plane. So see the product. So in the product, so both should be above, so CH2 CHO and CHO. So option C is correct. See, both are CHO. So minus 70 degrees centigrade, CN become CHO, not CWAs. After acidic workup, it become CHO. So the product, the stereochemistry of the product should be like that, option C. So this is in this option, acetic acid, carboxylic acid is there. Here also carboxylic acid is there. So option C is correct. So that's why the correct option is C. So I think you all are catching. I believe that you are catching all the points I am trying to show you, guys. All the mechanisms, all the use of reagents. So if there is any doubt, so you can comment in the comment box. So we will try to solve your doubts. So this is just a common use of reagents. So next, move to the next question. So this is chemistry concept booster 10. So this is a hemiacetal, cyclic hemiacetal. So these reagents are used. This is a phosphonium elite. So PCC also used. So PPHC, CBr4. So I think you can recognize this reagent in which reaction it is used normally. So we will see this is the reagent of core-fuse reactions. Again, diabalase come. See, this is not the minus temperature. This is normal room temperature or normal temperature. Then butyl lithium we use. So these are the option of the product. We will see the option. Just we see the starting material and try to write the mechanism, write the reactions, knowing our chemistry knowledge in chemistry, knowledge in reagents, knowledge in name reactions. So let's see the mechanism of the answer. So this is a hemiacetal. We all know this hemiacetal formation of a hemiacetal is reversible. So this is OH, this is aldehyde group. This aldehyde and OH group in presence of H plus form the hemiacetal, and this reaction is reversible. So we can write this hemiacetal like this hydroxycarbonyl compound. So in this hydroxycarbonyl compound, if we treated with this elite, so see, this is not a normal elite, this is a stable elite. See, in the there is negative charge in the C and positive charge in the P, and this negative charge adjacent to a CO2 group means electron withdrawing group. So this is a stable elite, stable phosphonium elite. So in presence of stable phosphonium elite, carbonyl group form E alkene. This is Wittig. Obviously, this is Wittig reaction. We all know this is Wittig elimination. But in this case, E selective means trans alkene, trans olefin, trans alkene will form. If we use, just keep in mind that if we use stable phosphonium elite, then trans alkene is formed. If we use normal phenyl phosphonium elite, then cis alkene will form. So this is also called Horner-Wittig reactions, where stable elite phosphonium elite is used and to form the trans alkene. So see, this is trans alkene. Now there is a hydroxy group. If we use PCC, this is a oxidizing agent, then hydroxy OH transform into aldehyde. PCC CH2Cl2, this hydroxy group transform into aldehyde. Now see, in this aldehyde we use Wittig elimination, or we can call Horner-Wittig reactions, that is E selective reactions. So again there is an aldehyde free aldehyde group. If we use PPHC CBr4, then there is a dibromo alkene formed. So this if we see the mechanism, so after this, if we use this molecule with if we treated this molecule with base in butyl lithium, then this step and this step, these two steps overall called core-fuse reactions. We will see the mechanism after some time. So now before the second step of core-fuse, they use a different reagent in this reactions to get a different kind of product. So see, first we will see the mechanism of core-fuse reaction. So this is the mechanism of core-fuse reactions. So it is the transformation of aldehyde to alkyne. So first CBr4 and PPH3, then we will get the dibromo alkene. After that, if we treat it with dibromo alkene with butyl lithium and work up, then we will get terminal alkene. So this is the mechanism. Since carbon is surrounded by 4 bromine group and bromine size of bromine group is very large, that's why PPH3 this will not attack the carbon center. This will attack the bromine center. So carbon center is surrounded by 4 bromine, large size bromine atom. That's why it cannot attack the carbon center. So it will attack the bromine center. This bond break. This CBr3 minus will form. This CBr3 minus will attack then the PPH3 plus Br. After this reaction, PPH3 plus Br will form. Then this will attack this PPH3 Br. then PPH3 plus and CBr3, this intermediate will form. Then this Br minus or PPH3 from the reaction medium will attack another bromine atom to form the PPH3 plus CBr2 minus. This is the elite, phosphonium elite. So now if we treat it with carbonyl compound, this phosphonium elite react like in a Wittig reactions, same as Wittig reactions. This minus attack this carbonyl carbon, and this oxygen attack this positive charge. So this is the intermediate, cyclic intermediate form. Now PO bond, since PO bond is stable, it will break in that way. So PPH3 will release. So phosphine oxide will be released because PO bond is stable. So in that stage, dibromo alkene compound will form. So from dibromo alkene compound, there is possible 2-3 mechanism we can obtain the alkene. So some people prefer this mechanism. So if we use butyl lithium, then butyl lithium will attack this hydrogen. There is negative charge, and the negative charge push this, and one bromine release. Then we will get R triple bond Br. Butyl, if we use butyl lithium, then halogen exchange will occur, Br lithium, then halogen exchange will occur with lithium. After workup, we will get alkene. Some people prefer this mechanism. So when butyl lithium, first lithium halogen exchange will occur, butyl lithium. So butyl bromide will leaves, and lithium and in that case butyl minus will attack this bromium, and there is negative charge. So this negative charge, in that case alpha elimination will occur to form a carbene like, and in that case this hydrogen transfer will occur to form the alkene. So last step, some people prefer this mechanism, some people prefer this mechanism. So this is the core-fuse reactions. From aldehyde we will get terminal alkene using CBr4 carbon tetrabromide phosphine triphenyl phosphine, then butyl lithium, and workup. So in this, the first step is okay, Wittig reactions, transalkene, then PCC oxidation, then in this case not the complete core-fuse reactions, the partial core-fuse reactions, dibromo compound will form. Then they use dival H, hexane CH2Cl2 workup. Then this ester group transform into then there is a ester group, so it's transformed into OH group. So dival H reducing agent, it's transform ester to aldehyde. In this case, this ester group transform into a hydroxy group, not aldehyde, hydroxy group. So after that, the second step of core-fuse reactions, will occur in this step, in this last step. So second last step. So then if we use excess in butyl lithium, then this in either mechanism, we saw just that there is two mechanisms. Either mechanism, this alkyne lithium is formed, and after workup this alkene is formed. So the correct option is this become alkene, and there is on hydroxy compound, on hydroxy group is there. So this is the product. So this is first step of core-fuse, this is second step of core-fuse. In the middle they use a different reagents to reduce the ester to alcohol. So this is the product. So we can see there is a alkene, and obviously on methyl group and then CH2OH. And obviously the stereochemistry, the CH2OH trans to this bond, not cis. See in the option C and D, option okay, there is no problem. So in C options, see this CH2OH should be trans to that double bond. So in this case, CH2OH is cis to the double bond, methyl is there, but bromine is there, so bromine should not be there, H should be there. So option C is correct. This is the stereochemistry, because from first step this is trans alkene, so this is trans ester. Trans means this bond and this bond trans. After first step of Corey-Fuse reactions, no change in this stereochemistry. So after reduction, this CH2OH should be trans to that double bond. So in the final product, CH2OH should be trans to that this bond. So the alkene is, at the final product, the alkene is trans in trans alkene, or you can say E alkene. So this is the product. So the option C is the correct answer. So let's move to the next question. So this is the chemistry concept booster 11. So this is a 3,5 di 3,5 there is diester hydroxy. So this is hydroxy. So allyl bromide is there, NN dimethyl aniline hate. So BNBr means benzyl bromide, and last aqueous NaCO3 Br2 CaCl3. So these are the reagents. So let's see the mechanism of the reactions. So this is the starting material. So first allyl bromide is used. So K2CO3, it's deprotonate the OH. So OH minus attack this. So this compound is formed, and we all know this is the allyl phenyl ether. So allyl phenyl ether is a perfect starting material for Claisian rearrangement. So this is, in that case you will see that NN dimethyl aniline. So we can most of the people will have some confusion, because they might think that what is the use of this reagent. So this is the solvent. So in that case, NN dimethyl aniline is just a solvent. So if we hit this compound, then 1 2 3 1 2 3, you all know the Claisian rearrangement. So allyl phenyl ether is a perfect starting material for Claisian rearrangement. So Claisian rearrangement will be Claisian rearrangement will occur in this step, second step. So we will get this product X. We will get X. So we will get this product. Now if we treated benzyl bromide, so PA is CH2Br. Benzyl bromide means PA is CH2Br. So K2CO3, it will again deprotonate the OH. So O minus will attack that PA is CH2Br, CH2 position. So we will get OBN. So we will get this product. Now they use sodium hydroxide THF, again aqueous HCl, means base use hydrolysis, then aqueous HCl workup. So this ester group hydrolysis to carboxylic acids. This is a hydrolysis step. This, after using NaOH, this ester become carboxylate anion after hydrolysis, then after aqueous workup, acidic workup, become carboxylic acids. Now last step they use aqueous NaCO3 Br2 CaCl3. See, I told you, I think in the first question we saw that if there is a alkene part in the molecule, if we use sodium bicarbonate and halogen like bromine or iodine, then cyclohexylonium ion form. In this case, cyclobrominium ion form. In that case, cycloiodinium ion was formed, but in this case, cyclobrominium ion is formed. So we use sodium bicarbonate. So sodium bicarbonate deprotonate both of the carboxylic acid, but since this carboxylate anion is closer to this and there is a possibility to attack via SN2 path, so this O minus attack this carbon to form a six membered lactone. So this CH2Br, so this will not attack because this is far from this this cyclobromonium moiety, this is far from, so this O minus attack this. Here second, this is called halolactonization reaction. So this is six member lactone. We already I already told you that for second or third questions, in our second or third question, so 5-member lactone is more stable than 6-member lactone, but here is the possibility of 6-member lactone formation or 7-member lactone formation. Obviously 6-member lactone formation is more stable than 7-member, that's why here 6-member lactone is formed, not 7-member, but 5-member lactone formation is more favorable than 6-member lactone formation. Here is no way to form 5-member lactone, that's why 6-member lactone is formed. So this is the product, this O minus attacked this and this bond break, so CH2Br, this will be the product. OBN should be there, carboxylic acid should be there, and this is there is a 6-member lactone with CH2Br. So sorry guys, sorry for some inconvenience. So so you can all see that and you can also see that this options are not for this reaction, so I did so some mistake, I think. So these options for these options are for different questions, so sorry for that, extremely sorry. So yeah, I think I did not set the options, I forgot to set the options, so I think that will not create any problem, but so just focus for the answer. So just see the reagent, just focus on the starting material, reagent, and how we can use the reagents, and in this whole reactions Clayton rearrangement we can see the use of Clayton rearrangement, halolactonization. So sorry for that. So next, so move to the next question. So I forgot to put the options for that reactions. So Clayton rearrangement is there, and that halolactonization, so to form a 6-member ring, not a 7-member ring. So this is the second 2 point is there, Clayton rearrangement, and second is halolactonization to form a 6-member ring. So move to the next question. So this, for these questions the option, so I mistakenly put this options for that question, so sorry for that. So now, so this is the chemistry council booster 12. So this is amide, so amide, so we, the reagent is s-butyl lithium TMEDA BOMe3 whole 3. So this is, you can see, or you can all see that this is the reagent of some coupling reaction. So see, let's see what is the coupling reactions. So at first LDA and then acetic workup. So this is the starting material. Let's see the every steps and try to understand the mechanism in every step, which REM reactions, which rearrangement, or which reagents are used. So let's see. So this is the amide is given, and s-butyl lithium. So s-butyl lithium is a strong base. So we all know that if there is CO, OMe or Ne2 or other types of particularly normally N and O, nitrogen oxygen like group is there, then ortho of that hydrogen will be abstracted by butyl. So this is called regioselective ortholithiation. So if there is a group like nitrogen oxygen COOMe or CON82 which can complex with lithium in such a way, then ortholithiation, just ortho, there is two ortho hydrogen, 1 2, any one of them, ortholithiation, this hydrogen abstracted by this butyl lithium and lithium is attached with this, means there is negative charge. So this is called regioselective ortholithiation. So I think many of you already know this regioselective ortholithiation. So this is called regioselective ortholithiation. If there is a group which can complex with the lithium ion, particularly nitrogen and oxygen, COOMe or CONNR, so in that case we will get ortholithiated product. So now there is a negative charge, so this ortho hydrogen abstracted by the base. So now BOMe3, so BOMe3 is there. Now this is there is negative charge, so this negative charge will attack this boron atom and one OMe leaves as OMe minus or as a to form leaves as methanol OMe group. So OMe group leaves as a OMe minus, it will abstract on hydrogen from the reaction medium to form methanol. Now the product is CONe2 BOMe whole 2. So BOMe whole 2, if we use the if we did hydrolysis of this compound, then only BOMe3 become BOH2. So amide group in presence of water, amide group cannot hydrolyze. Amide group cannot hydrolyze. It is less reactive. So amide group still there in the product, but BOMe2 become BOH2. Now see this BOH2. If we use a phenyl, this is orthomethyl bromobenzene. So this is RX. You can assume this is a RX. X mean halogen. So palladium PPH3 sodium carbonate. So this is Shojogi coupling reaction. So this product, if there is BOH2 and there is a RX moiety in presence of palladium catalyst, then Shojogi coupling will happen. Shojogi coupling will happen. There is so many coupling, Shojogi, so Sono-Gashida coupling, so Heck coupling. So in this case, since there is BOH2, that's why Shojogi coupling will occur and this BOH2 group replaced by this brominium. So in that case, in this whole group will attach in that case, in that space where BOH2 will attach. So we will get this product. So at last, if we use base, since there is a benzylic position, means methyl, in this methyl, you can say this methyl is a benzylic position. So benzylic hydrogen are acidic hydrogen. So in presence of LDA, this methyl group deprotonate, so CH2 minus will form. So LDA abstract from hydrogen from this methyl, that is a benzylic position. So benzylic deposition will occur and this CH2 minus will attack the amide carbonyl carbon and release, and this tetrahedral intermediate will form. Now if we hydrolyze this moiety, then via iminium ion formation, so via H plus first protonate this OH plus, then the lone pair nitrogen push that and OH2 plus leave as water, then the iminium ion is formed. In presence of water, that iminium ion hydrolyzed to form carbonyl compound. See, this is the product of carbonyl compound after hydrolysis of iminium ion. Now this is a carbonyl ketocarbonyl compound. It will tautomerize to a hydroxy. So enone, this is ketone, this is enol. So keto-enol tautomerization. This enol form is more stable because this is aromatic. This enol form is more stable because this is aromatic. keto-enol tautomerization. In this case, normally keto form in normally keto form, in most of the case we see keto form is more stable than enol form, but in that case, since after converting enol form the whole system become aromatic, that's why in that case enol form is more stable, and this whole moieties exist as this form, enol form. So this is the final product. So the final product is B. So there should not be any methyl group in that case. So you cannot stop in that compound, because if you stop in that compound, then there will be no option match with this compound. We have to see there is two benzene group which are aromatic. If there is a keto and alpha hydrogen is there, so there is possible of keto-enol tautomerism. So after tautomerization, the enol form become, the whole system become a phenanthrene nucleus. So this whole nucleus become a phenanthrene nucleus, which is aromatic compound. So that's why in that case this compound will exist only in the enol form due to attaining aromatic stability. So the correct option is D. Option B is the correct answer. Next, move to the move to the next question. So this question is cyclohexanone is given. 1, 2, 3, 4, 5 reagents are given. So PaCH2Li. So MCVBA, use of MCVBA, POCl3, N-butyl lithium, and then sodium amalgam. So these are the options. Later we will see the options. First we will try to treat every reagent in that compound and try to understand the mechanism, and let's see. So cyclohexanone, if we PaCH2Li means PaCH2 minus is there. So this CH2 minus will attack this carbonyl compound CH2. So after aqueous workup, OH will form. Now MCBBA, there is OH, there is sulfur group. If we use MCBBA, there is normal sulfur as a sulfide, then it will oxidize to sulfone or sulfoxide. So after treating with MCBBA, this SPH become SO2PH. So SO2PH, oxidation of sulfur will occur in this step. So POCl3 pyridine. So in that case POCl3, so pyridine will abstract first one hydrogen from OH. This O minus will attack this phosphorus atom and one Cl minus leave. Now that whole leaving group become OPOCl2. Now the whole leaving group become OPOCl2. First O minus attack this phosphorus, one Cl minus leave, then it will become POCl2. Again pyridine abstract this hydrogen, and there is a obviously anti-elimination. Obviously if we draw the Csir form, then anti-elimination will occur. So there is this type of alkene will form. So minus H2O. So so not as a minus H2O, but it will leave as a POCl2. So H POCl2. So after, this is not a good leaving group, so it will become first OPOCl2, then the elimination occur. So minus H2 is not a correct in this step. So in that case, so first OH become OPOCl2, a good leaving group, then the elimination will occur. So we will get after this kind of compound. So N-butyl lithium. So N-butyl lithium will abstract, this is allylic positions, and there is a sulfone group, or SO2 group, which is the electron withdrawing group. So this hydrogen is extremely acidic. So this butyl lithium abstract this hydrogen. Now this hydrogen will attack the aldehyde. See here, use benzaldehyde. Benzaldehyde attack the benzaldehyde. Now this moiety is formed. So if we treated this moiety with acetic anhydride, then this O minus will attack this. So OCOCH3 will form. Now if we use this compound, if we treat sodium amalgam, then sodium give 2 electron from this to sulfur, and this compound will form, and then one O minus push the electron, and this in this way this here negative charge is formed, and this negative charge push the OSC minus. So alkene is formed. So trans alkene is formed. So from X to Y. So this reagent N-butyl lithium, benzaldehyde, then acetic anhydride, then sodium amalgam. So it is called Julia olefination reaction. So in this, we get a Julia olefination reaction. We get Julia olefination reaction. So E-alkene, final product. So Julia olefination exclusively E-alkene selective reactions. So we normally get E product as an exclusive amount after Julia olefination. So so they can give any product. They can give product like that and treated with sodium amalgam. Then directly in this way we will get the olefin, trans olefin. So this is the from X to Y. This is the whole Julia olefination reaction. This is the whole Julia olefination reaction from X to Y. This is these 4 steps involved in Julia olefination reaction. So later we will see the Julia olefination reaction, Peterson olefination reaction. So in our upcoming video we will discuss details in the name reaction series. So for now, just note that Julia olefination reaction 1, 2, 3 in 4 step. Julia olefination reaction will give transalkene, and these are the reagent normally used in Julia olefination reaction. So this is the product. So we will get trans alkene, and in the cyclohexane double bond should be here. So this is the correct answer. This is cis alkene. This is also cis alkene, but double bond should be there. So option A is correct. So option A is correct. So here we will see the Julia olefination reactions. So let's move to the next question. So this is the questions. So this is the questions. Grignard, allylic Grignard reagent is used. Then workup. Then palladium chloride CuCl. So after seeing this reagent, you can recognize, I think, that the Walker oxidation reaction. We all know that this reagent are used normally in Walker oxidation. So let's see. These are the options. So see, there is a carbonyl compound. So normally in allylic Grignard reagent, this point has to be noted, that note that point. Normally allylic Grignard reagent do not react with this in allylic Grignard reagent, react with the remote to the magnesium atom, means where the magnesium atom attached, it will react in this way, remote to the magnesium atom end. So if there is allylic magnesium Grignard reagent, then this in where magnesium atom directly connected, this in will not react. The other in react with the carbonyl compound if there is allylic allylic Grignard reagent. So this bond break, and where the R atom is directly connected, this in react with that, and we will get this OMGBr. After workup, we will get this alcohol. Then in presence of H plus water, this OH protonate, obviously this OSI bond break, and in this way OH2 also lift. So here we will get this oxonium plus charge on oxygen atom. Now water will attack this SiMe3, this bond break, and we will get this aldehyde double bond. Here is double bond. So now if we use palladium chloride, so it will attack with the terminal double bond. There is two double bond. This is alpha beta unsaturated carbonyl, but there is a separate alkene part in this compound, so it will react with the separate alkene part. So not the alpha beta, this alkene part will not react with palladium chloride, only the terminal or the separate alkene part. So in this way Walker oxidation will occur. So here is the mechanism of Walker oxidation reaction. So palladium chloride coordinate with the double bond, then water will attack this carbon, not the terminal on, the internal on, and then OH will form, and then beta elimination will occur. So in this way beta elimination will occur. So hydrogen is there, hydrogen and PDCl, so leave, so to form a enol, then it will transform as a ketone. So now if we treat ammonia, then normally there is two COMe and COH, aldehyde and ketone moieties. So in both the carbonyl group react with ammonia, but since aldehyde is more reactive, so first ammonia will react with aldehyde to form a imine. Then this imine nitrogen attack the carbonyl ketocarbonyl to form like this intermediate, and after heating, water is removed to form this kind of structure. So in this case we learn the use of allylic Grignard reagents. It normally react with the remote position, not that position where the magnesium atom directly attached. And Walker oxidation, we learn also the Walker oxidation. So final product is that. So Me and R should be adjacent, and N should be the adjacent to Me. So R and Me adjacent, and nitrogen should be adjacent to the Me. So see, in the 4 option only option C is matched with the product. R Me adjacent, nitrogen is adjacent to the Me. R Me adjacent position, nitrogen is the adjacent to the methyl group. So this is the questions. So chemistry concept booster 14. So now let's move next question. So this is a farfural aldehyde. This is alpha beta unsaturated carbonyl. So if we use catalytic NaCN in DMF, so what will be the product? So now let's see the answer. So by saying there is NaCN, CN minus is a good leaving group. So one can easily imagine that there is alpha beta unsaturated carbonyl, so CN minus can attack there, and in this way here negative charge will be formed after returning the negative charge from this position, and this position will attack that carbonyl, but this is not the case here. So here first, since there is a aldehyde group, this compound name as farfural, so furan aldehyde farfural, so CN minus attack first this aldehyde group, then this tetrahedral intermediate will form, and this hydrogen become more acidic after attaching CN of that carbon. Now it will abstract by this OH minus. So this negative charge on carbon now attack the beta position of this alpha beta unsaturated carbonyl. So this intermediate will form. Now this OH bond break to form a carbonyl, and CN minus lift. In that case this double bond OH is there, and this enol become a carbonyl compound. So in that case CO should be there, PH should be there, and CH2COPH. So in that case, Cn minus does not attack this this beta position. It will attack first that carbonyl compound. Now the negative charge on that carbon will attack the beta position of that alpha beta unsaturated carbonyl, and after breaking the OH bond, there is a carbonyl group. Cn minus will leave, and this double bond means OH should be there. After workup, OH should be there. So this OH double bond become C double bond O. So the main product is, the final product is COPH, CH2COPH. So the final product is CO, CH2PH, CH2COPH. So this is the final product. So just one point have to be noted that Cn minus does not attack first that beta position of alpha beta unsaturated carbonyl. It will attack first the carbonyl compound, means aldehyde. Aldehyde is more prone toward nucleophilic attack. That's why then this negative charge will attack that alpha beta unsaturated carbonyl. So next move to the last question, and already the video will be 1 hour and 20 minutes. So let's move to the last questions. So this is the questions. So this is the allyl bromide, and this is the reagent. These are the reagent are given. So allyl bromide, sulfur 1,3-dithiene is there. So sulfur nucleophile will attack this allylic bromide. So this intermediate will form. Sulfur is there. Sulfur is there. So butyl lithium is, if we use butyl lithium, then there is two sulfur. One sulfur has positive charge, one sulfur is there. So between these two sulfur, the hydrogen is more acidic, because there are two sulfur atom in adjacent to this hydrogen, and one sulfur is in positive charge. So this hydrogen become more acidic, and this hydrogen is abstracted by butyl lithium. So now see 1 2 1 2 3. So this compound is, this ylide, sulfur ylide, is a perfect starting material for sigmatropic reaction. This type of reaction you can also call Stevens rearrangement. So this 2-3 sigmatropic reaction will happen. So we will get this type of product. So this bond will break, one break, we will get this type of product. So after hydrolysis of 1,3-dithiene, we will get this type of product. So alpha beta unsaturated aldehyde, but the double bond should be exocyclic, not within the ring. So in the option D only, the double bond is exocyclic, and so the D is the correct answer. So here 2-3 sigmatropic rearrangement, or you can say Stevens rearrangement, is will happen in this A reaction. First the sulfur ylide will form. Sulfur nucleophile attack this carbon, bromine left SN2 attack. Since there is two sulfur atom adjacent to this hydrogen, one is positive charge, that's why this hydrogen become more acidic. In presence of base, this hydrogen abstract, and this whole compound is a perfect starting material to proceed sigmatropic rearrangement. So that's why we will get this product. So I hope you all understand 10 questions. Just we discussed every step. We learned use of some reagent. We learn also some name reactions during discussions. So I hope this practicing of this 10 questions from organic chemistry will help you a lot, and will improve your concepts in organic chemistry, and will boost your power to solve different type of organic chemistry. So thank you for watching. I believe this video will help you a lot for upcoming CSIR NET, GATE and Barc exam. So thank you again. So stay safe, stay healthy.